How do these things work? I'm going to explain first what happens in an LC circuit. Let's say we've got a circuit like that. That's an LC circuit. Let's assume this capacitor was fully charged. It was charged positive, negative. And we connect the capacitor in this circuit. What is going to happen? The capacitor is going to discharge through the coil. You agree? When it discharges, we set up a magnetic flux. All right. What's going to happen? The magnetic flux is going to collapse. When it collapses, it's going to generate an EMF with the opposite polarity. That means the polarity will be positive, negative. All right. We will charge the capacitor then. Charge the capacitor positive, negative. What happens again? Capacitor again discharged through the coil, setting up a magnetic flux. Now, if we had an ideal inductor and an ideal capacitor, that means the energy from the capacitor to the inductor or the coil and from the coil to the capacitor will be exactly the same, and that thing should oscillate forever. All right. Now, what happened in practice is the following. That thing will do that, and the oscillations will slowly die away. That means the frequency is going to be constant, but the amplitude will start decreasing due to the losses. All right. Now, all these oscillators we're going to do in this part of the chapter is LC oscillators. How do they work? They got an LC resonance circuit connected to an amplifier. All right. What's the purpose of the amplifier? To just overcome the losses. All right. That means if you have to study it, go and look at all the different feedback circuits and you know an amplifier. All right. Very simple. That brings us to the first oscillator, our LC oscillator. That is the Colpitts oscillator. Now, if you look at this part here, what is that? That's a normal common emitter amplifier, all right. Electronics 2, a common emitter amplifier, and that is connected to my feedback circuit. What is my feedback circuit? This feedback circuit is called the Colpitts. I always tell the students, think about Colpitts capacitor. It will have two capacitors and one coil, all right, or inductor. Two capacitors, one inductor, then you know it's a Colpitts. We're going to look at the Hartley oscillator. The Hartley will again have two inductors and one capacitor. All right, just the way to remember. All right, there's my oscillator, amplifier with my feedback circuit. Here's the formula for my resonant frequency. FR is equal to 1 upon 2 pi square root of L times C total. Now, capacitors in series act like what? Resistors in parallel, all right. Just remember that when you go and do your calculations. Here's all the formulas for this circuit. As I already mentioned, C total is equal to C1 times C2 over C1 plus C2. Also engineering 1. Here's my attenuation. My feedback voltage divided by my output voltage. And when we put XC, I times XC will give me that, XC1, and I times XC2 will give me my output. And when we work it out, we can say my attenuation is equal to C2 divided by C1 because all those things are going to cancel out. Now, as they say, as you know, the condition for oscillation is the voltage gain times my attenuation should be equal to 1. It still apply, all right. And my attenuation is equal to C2 divided by C1. Gain is also equal to C1 divided by C2, all right. Here they just show us about the attenuation. Where is V out, where is VF, and there I got an amplifier and my feedback circuit. Then they're also going to tell us for starting up conditions, the gain must also be a little bit larger than 1, all right, for starting up conditions. Now we're going to talk about loading effect on the feedback circuit. They say it will also affect the frequency of an oscillation. And that will also be determined about my Q factor. If I got a Q factor larger than larger than 10, my frequency is basically going to stay the same. But if my Q factor is smaller than 10, then it will have an effect on my resonant frequency. They say there, as indicated in figure 16.18, the input impedance of the amplifier acts as a load to the resonant feedback circuit and reduces the Q of the circuit. The resonant frequency of the parallel circuit depends on the Q according to the following formula. All right. Now, if I got a Q factor smaller than 10, then I must use this formula. Right. Why? Because it will have an effect on my resonant frequencies. They say a rule of thumb, with a Q greater than 10, the frequency is approximately equal to 1 upon 2 pi square root of L times C total, as stated in equation 16.5. When Q is less than 10, however, FR is reduced significantly. All right. That means my Q factor or my resonant frequency will be influenced by the loading effect. All right. If I load the resonant circuit, it will reduce my resonant frequency. All right. Everybody with me? Yes. Any questions? Now, there are certain things that we can do to basically minimize that problem. That brings us to the next circuit. All right. First of all, if I ask you to name this circuit, what will you name that circuit? Electronics 2. What are you saying? All right. This is a self-biased JFET amplifier. Self-biased JFET amplifier. What's the big advantage of a self-biased JFET amplifier? What is the biggest or the largest advantage of that amplifier? Anybody of this brilliant electronics 3 class? Huh? All right, you've got a very high input impedance. This input impedance is very high, and that will be normally determined by R1. We normally choose R1 very high in the meg ohm range. All right. That means I'm not going to load my resonant frequency. That means now you get rid of the loading effect that can exist. All right. You with me? All right, on the output side, we can also load my resonant circuit. They say a load capacity coupled to the oscillator output can reduce the circuit Q and FR, my quality factor or my Q factor and my resonant frequency. If it's capacitively coupled, I can also load my resonant circuit. What we can do, we can make use of transformer coupling to reduce the loading effect by impedance transformation. That means by doing that, I can reduce the loading effect on my resonant circuit. All right. Yes. That means we had two problems. The first problem was the loading of the resonant circuit due to the input impedance. All right. We can reduce that to go and look at a JFET self-biased amplifier. And then we also had the loading effect also on my resonant circuit due to a capacitively coupled to the load. We can also reduce that by making use of transformer coupling there. All right, let's have a look at the next example. Example 16.3. They say determine the frequency of oscillation in figure 16.21. Assume there is a neglectable load on the feedback circuit and that Q is greater than 10. Then B, find the frequency if the oscillator is loaded to the point where Q drops to 8. Alright, that means we're going to use two different formulas to determine my resonant frequency. Alright, there's the circuit. You can see it's a Colpitts oscillator. Got an amplifier. First of all, we assume Q is larger than 10, and then we work out our resonant frequency and get a value of 7.46 kilohertz. Then we're going to assume my Q is 8, my quality factor is 8, and we work out, and then we get a resonant frequency of 7.4 kilohertz. You can see when you start loading the circuit, the resonant frequency is going to decrease. All right, now we're going to look at the clap oscillator. Now the clap oscillator is basically a modification of the Colpitts, right? It's going to be a modification of the Colpitts. I just wanted to show you what we do when we can look at the clap oscillator. In the case of the clap oscillator, what we do, we add additional capacitor in this LC circuit. Here, in that circuit, we add an additional capacitor. All right. The value of this capacitor, we make it normally much smaller than the capacitor values of C1 and C2. All right. But that is a clap oscillator. It's also basically a Colpitts, but we add C3. Now we're going to look at what is the advantages when we add C3 to that circuit. They state the clap oscillator is a variation of the Colpitts. The basic difference is additional capacitor C3 in series with the inductor in the resonant feedback circuit as shown in figure 16.22. Since C3 is in series with C1 and C2 around the tank circuit, the total capacitance is, all right, C total is equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3, all right. Then they say, and the approximate frequency of oscillation, when Q is larger than 10, resonant frequency is 1 divided by 2 pi square root of L times C total. But now here's the big important story. They say if C3 is much smaller than C1 and C2, and C3 almost entirely controls the resonant frequency. Why? If I put resistors in parallel, all right, what determines normally the total resistance? The largest resistance or the smallest one? The smallest one. Now in this case, exactly the same. The total capacitance will be basically equal to the smallest capacitor value. It will be a little bit smaller, lower, but actually that will be the capacitance value. They state there, if C3 is much smaller than C1 and C2 and C3 almost entirely controls the resonant frequency, if R is equal to 1 upon 2 pi square root of L times C3. Since C1 and C2 are both connected to ground at the one end, and the junction capacitance of the transistor and other stray capacitance appear in parallel with C1 and C2 to ground, alternating their effective values. C3 is not affected, however, and thus provides a more accurate and stable frequency of oscillation. That means this type of connection will give us a much accurate and stable frequency. And the frequency will basically be determined by the value of C3. And when you design a circuit like that, you will make C3 much smaller than C1 and C2. All right. Everybody with me? All right, there's your circuit diagram of the clap oscillator. Then we go to the next one, the Hartley oscillator. Now, as I already mentioned previously, in the case of the Hartley oscillator, we will have one capacitor and two inductors, or two coils. All right, there's one capacitor and two coils. Here is my resonant frequency, 1 upon 2 pi square root of L total times C. All right, my total inductance will be determined by add L1 and L2. It's not like capacitors, we're going to just add them. That means L total is going to be equal to L1 plus L2. My attenuation is going to be equal to L1 divided by L2. My voltage gain is going to be L2 divided by L1, L2 divided by L1. And that brings us to the next oscillator, also an LC oscillator, and that is called my Armstrong oscillator. Now, in the case of the Armstrong oscillator, again, as I already mentioned, we got an LC circuit connected to an amplifier. Now, we know the phase shift between this input and the output of the amplifier is how many degrees? How many degrees phase shift between the input and the output? What are you saying? What are you saying? How many degrees? 180 degrees between the input and the output. In the case of a common emitter amplifier, I got 180 degrees. Now you can also notice here, this transformer is also coupled that there is a 180 degrees phase shift here. Those dots indicate 180. If there was a dot there and there, then it gives me 0 degrees phase shift. But now I got a dot there and there, 180. That means I get positive feedback, and that is basically my Armstrong oscillator. All right. 180 degrees across the amplifier, and here we also got another 180, and that will give me positive feedback. All these circuits, we got basically a LC circuit that will oscillate. There is losses. You must just make the gain of the large enough to overcome the losses. All right. Any questions? Now we're going to talk about crystal controlled oscillators. Crystal controlled oscillators. Is there any crystal controlled oscillators in this classroom? I'm asking, is there any crystal controlled oscillators in this classroom? Yes or no? All right. Answer is yes, some say no. Where? Show me a crystal controlled oscillator here. No. Maybe, but... Huh? All right, the watch. Yeah, I got a watch. All of you got electronic watches today. Now, in these electronic watches, how do they work? If you look at some of them, I think that one, if you read there, they're in quartz. Why do they write quartz there? Why do they write quartz? There's a quartz inside. All right, there's a quartz crystal inside the watch, all right? And that is going to work as an oscillator. Now, why quartz as an oscillator? Because that will give me a quite accurate, stable frequency, especially if you keep the temperature constant. Now, normally your watch, you normally got it in your body, and if you're a wealthy person, your body temperature will be fairly constant, and and that's why that quartz crystal will give us quite an accurate frequency. All right. How did the old watches work? For interesting, the old watches, they had a spring, you wind it up. How did they work? How do they get their oscillation? From where was that oscillation coming? Anybody? No, the wind was just like a battery. How does this watch work? What is powering this watch? A battery, right? How's your, the old watches, how did they work? Their battery or the energy was coming from a spring. You wind up a spring, that means it was mechanical energy. You store basically mechanical energy in that spring. Yeah, but where does the oscillation come from? Are you engineering students? You engineering students? What do you know? Nothing. No. Now I'm asking you a very simple question. Is there nobody that can answer me? Huh?
It's all about mechanics. It's what like it stores energy via mechanical energy. Therefore,
Yeah, you store the mechanical energy, but I'm asking, yeah, what is the energy here? It's a battery. But where does the oscillation come from? It comes from the crystal, all right? But in the normal old watch, where does the oscillation come from? No. It had a flywheel. That thing was doing that. And that flywheel, due to that movement of the flywheel, was giving the time. All right. The flywheel was doing that, was oscillating. That flywheel was actually oscillating. Go and have a look in a book and go and read a little bit and you'll find out. All right. You also get something, they call it electronic lighters, but some of them are not an electronic lighter. What they use there, they use a quartz crystal, and they got a small hammer. And when the hammer hits the crystal, it basically transforms mechanical energy to electrical energy to give a spark. You get some of these lighters, it gives a spark. How does those things work? You press like a trigger and it says click. And that means the mechanical hammer hits the quartz crystal and basically converts that to electrical energy. All right. But here we can also use a quartz crystal. They say the most stable and accurate type of feedback oscillator used piezoelectric crystal in the feedback loop to control frequency. Now, quartz is basically a substance we find in nature. All right. How do they create a crystal? They cut it to certain dimensions. All right. We will come to that. They say the piezoelectric effect quartz is one type of crystalline substance found in nature that exhibits the property called the piezoelectric effect. When a change in mechanical stress is applied across the crystal to cause it to vibrate, a voltage develops at the frequency of the mechanical vibration. Conversely, when an AC voltage is applied across the crystal, it vibrates at the frequency of the applied voltage. The greatest vibration occurs at the crystal's natural resonant frequency, which is determined by the physical dimensions and the way the crystal is cut. Crystals used in electronic applications typically consist of a quartz wafer mounted between two electrodes and enclosed in a protective can as shown in figure 16.25a and b. A schematic symbol of the crystal is shown in figure 16.25c. An equivalent RLC circuit for the crystal appears in figure 16.25d. As you can see, the crystal equivalent circuit is a series parallel RLC circuit and can operate in either series resonance or parallel resonance. At the series resonant frequency, the inductive reactance is cancelled by the reactance of C3. The remaining series resistor RS determines the impedance of the crystal. The parallel resonance occurs when the inductive reactance and the reactance of the parallel capacitance CP are equal. The parallel resonant frequency is usually at least 1 kHz higher higher than the series resonant frequency. They say a great advantage of the crystal that it exhibits a very high Qs or values of several thousands are typical. An oscillator that uses a crystal in a series resonant circuit shown in figure 16.26a, the impedance of the crystal is minimum at its series resonant frequency, thus providing maximum feedback. The crystal tuning capacitor CC is used to fine-tune the oscillator frequency by pulling the resonant frequency of the crystal slightly up or down. Now, if you look at this, let me just move it a little bit down. You find some big crystals, they're in a fairly big protective can. There's the basic construction. You can see there's two electrodes and there's the crystal wafer, the way it's cut. There's a symbol of a crystal, and here's my electrical equivalent circuit of the crystal. Now, if you take, for example, a crystal like that in a mechanical can, you put it on a scope and you give it a mechanical shock, that thing will give you a nice sine wave out. It will give you a wave out, but you will also notice the wave will die away. Because when you heat it, you basically apply mechanical energy, and that's going to be converted to electrical energy. It's going to basically resonate at that. One problem, we can't go to too high frequencies, because what happens? You can only cut that crystal to certain dimensions. And the thinner you make that slab, the higher the resonant frequency, all right? But the nice thing about a crystal, we've got very high Q values, and due to these high Q values, your resonant frequency is quite sharp. All right, if you look at this, here is basically crystal oscillators. Again, amplifier with the crystal in the feedback circuit. Talk about CC, the tuning capacitor. The first electronic watches you could have buy. Most of this ones today got a liquid crystal display. Why a liquid crystal display? Because the power dissipation is very low, right? But the old watches had LED displays. That means they used much more power. And there they had a small tuning capacitor. That crystal looked like the lead of a pencil. You know, a normal pencil, the lead was around about, let's say, 2 millimeter or 1 millimeter in diameter, small thing with two wires, and then you also had a tuning capacitor to fine-tune the old watches. Today, they put some of these crystals inside the IC and things like that. You won't even see the crystal. All right, there's the two crystal controlled oscillators. Then we're going to talk about modes of oscillation of a crystal. Now, one thing, around about the upper limit, what they can get out of a crystal, the way they cut the crystal is around about 20 megahertz. That means crystals, we can't go higher than 20 megahertz because the way they cut the crystal, they can't cut it too thin, then it's going to basically splinter and it's going to break, all right? They can cut them fairly thin. But now, to go to higher frequencies, we're going to look at our fundamentals, right? Fundamental frequencies, then you can go to much higher values. They say piezoelectric crystals can oscillate in either two modes, fundamental or overtone. The fundamental frequency will be basically, if you buy a crystal and they say it's a 1 megahertz crystal, that'll be the fundamental frequency, all right? The fundamental frequency of a crystal is the lowest frequency at which it's naturally resonant. The fundamental frequency depends on the crystal's mechanical dimensions, type of cut, and other factors, and is inversely proportional to the thickness of the crystal slab. Because a slab of crystal cannot be cut too thin without fracturing, there is an upper limit on the fundamental frequency. For most crystals, the upper limit is less than 20 megahertz. For higher frequency, the crystal must be operated in our overtones. All right, say operate in the overtone mode. Overtones are approximate integrals of multiples of the fundamental frequency. The overtone frequencies are usually, but not always, odd multiples, 3, 5, 7 of the fundamental. Many crystal oscillators are available in integrated circuit packages. That means you can go and buy an integrated circuit package and there will be a crystal inside that package. All right. Any questions? All right, that's enough for today. Next time we will look at 16.5, the relaxation oscillators. All right.